Good afternoon. All right. All right. Oh, yeah, you can't really see that, can you? Oops, wrong button. There we go. All right, here we go. Sorry about that. We are on section 4.6, graphing log functions. So we graphed exponentials, and I don't know if you remember that because it was a while ago now. I said we could make a real easy XY chart and graph them pretty easily, and then shift using H and K. And so we're going to do sort of the same thing today, and I'm just going to do this without her instructions here. I want to graph the function, and identify some key characteristics. This is a very basic function, so before I begin, I have a generic equation that we're going to do. F of x equals a times log base b of x minus h in parentheses, and then a plus k on the outside. This is a really generic function. And just like we did with graphing exponentials, we can actually, it's really easy to graph the core function, the parent function, the core, a log base b of x. So this is the core function. And so what we're going to do is we're going to create a real easy table of values. That turns out to be really easy. And then I can shift it, h units. What does the h do? Left or right. Yeah, that's going to go left or right. And then what does the k do? Up or down. Yeah. And so that's what we're going to do. We're going to have two graphs. One is the basic graph, and then the shifted, the actual graph. Now, log functions, it turns out, are really easy to graph using some very specific values. Anytime you have a basic log graph, we are going to use, for our x values, we're going to do the log of 1. Because what's the log of 1? 0. The log of 1 is always 0, which I'll talk about again, just to remind you. And then we're also going to use whatever the base happens to be. So if my base is 3, I'm going to use that as a value as well. Okay? So we're always, we're going to use 1 and the base, whatever those happen to be. So I'm going to go ahead and I'm going to plug in my value of 1 here. So that's going to be log base 3 of 1. Again, how do you drop a log, ladies and gentlemen? Give it a swirly, right? So this is saying 3 to what power equals 1? 3 to what power equals 1? 0. 3 to the 0. 3 to the 0 equals 1 every single time. So again, we're refreshing our brain on how logs work. Now, log base 3 of 3 equals our y value. 3 to what power equals 3? 1. Yes. So 3 to the first power equals 3. All right? What we did was create some real easy ordered pairs. I have the ordered pair 1, 0, and I have the ordered pair 3, 1. Okay, so what does this function look like? I only have 2 values here, but you're right. This function is the opposite, the inverse of the exponential. The exponential had a horizontal asymptote. What's this one going to have? A vertical asymptote. So it has a vertical asymptote, always. In this case, it's starting here at x equals 0. And then I'm going to discuss my log right. Question? Yeah. So an exponential graph we know is the Superman graph. It grows really quickly. Superman to the moon, right? So log. I like to think about a log graph as a log ride at an amusement park. Okay? Well, so no, not exactly. Just the beginning of a log ride. And every single log ride, you wait in line forever, and then you get in the little boat-type vehicle vessel thing. What is the very first thing that every single log ride does? It goes up. You have to go up every single time. So, ladies and gentlemen, you go up, and it's almost like straight. It's up, 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 up. And then you get to the top, and then it's like, it's a small world after all. It's like the boringest ride ever, right? Boringest ride ever. Until the very end, like Pirates of the Caribbean. But other than that, that's the log ride. You go up, and then you go, it's just boring. So, this is what the log graph looks like. I love them, actually, but you go up, 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 and then it's just the boringest ride. Almost vertical, and then it just peters out. It is the slowest growing function there is. It is super slow. So every log ride has this shape. What would happen if there was a negative in front of this log ride? It flips vertically. So then it'd be going down, 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 and okay? So keep that in mind. So this has an asymptote, a vertical asymptote at x equals 0. Very important, we have a vertical asymptote. And you'll notice there's nothing over here in negative land. What is the domain of this function? 0 to infinity. Does not equal 0. We get close, but not touch. And then it exists to the right. So from 0 and to the right. So from 0 to infinity. What's the range, though?
Negative infinity.
Negative infinity to positive infinity. It does continue to increase forever. So eventually it's going to get up there, but it does go low forever and high forever. And that's really all I care about. Let's look at...
What's the one called where it's vertical and a horizontal asymptote?
Those are going to be rational functions. Let's do... Well, sure, we can do this one as well. We have log base 1/2 of x. Again, this is a very basic function. I'm going to create my little xy table of values. What values am I going to choose for x? 1 and 1/2. Whatever my base is, that's going to be a good choice. So I'm going to plug in my value of 1. Log base 1/2 of 1. So 1/2 to what power equals 1? 0 every single time. And now if I plug in the 1/2, log base 1/2 of 1/2 equals 1 every single time. Why? Well, yeah, by itself. Yeah, you're going to get a 1. If you give it a swirly, does it make total sense? Absolutely, right? So now we can graph. We have 1, 0, and I have 1/2 up 1. Oh, 1/2 up 1. Oh, so that's right there. All right. What's this one doing, do you suppose? Yeah, it's a decreasing function. We still have that vertical asymptote at x equals 0. But yeah, this is a going down, decreasing log ride. All right. Do you have questions so far? Is this okay? All right. Turn the page. I don't want to do this one. Let's do f of x equals log base 4 of x plus 3 minus 2. Log base 4 of x plus 3 quantity minus 2. Yeah, So this has more complicated things. This has an h and it has a k. We're going to just graph to start this basic part right here. And I'm going to just graph the core. I'm going to create my very simple XY chart. What is good choices for x here? 1 and 4 every single time. All right, what's log base 4 of 1? 0. The log of 1 is 0. What's log base 4 of 4? 1. All right, so we have ordered pairs 1, 0, and 4, 1. And I'm going to go ahead and sketch in use a dotted function here. This is my basic function. My log right, it goes up, 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 and then fizzles out. And then from here, I have 2 good values, and I get to shift them. How is this going to be shifted? Left 3 and down 2. So I'm just going to take my ordered pairs and count them left 3 and down 2. Left 1, 2, 3, down 2. Plot the point. Left 1, 2, 3, down 2. Plot the point. What happened to my vertical asymptote if I'm shifting this graph to the left 2? Yeah, left 3. Sorry, you're right. We're shifting it left, so that vertical asymptote is shifting left 3. So we want to draw in that vertical asymptote first. X equals -3. And now you can draw your log right. It goes up, 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 and then sort of fizzles out. And if you make the sound effect, it's way cooler. All right. What's the domain of this graph? Not -4. -3 to infinity. Perfect. What's the range? Negative infinity to positive infinity. Beautiful. That's all I care about. Do you think you get that? Yeah? Okay. I'm going to give you, we're not done with notes, but I'm going to give you about 4 minutes to practice graphing these easy ones. And then I have a couple more I need to do. So I'm going to give you about 4 minutes, maybe 5.
Just the ones on the bottom.
Yeah. Of course, they're not that easy, but I wanted you to get the hang of the easy ones. Let's do one that is a little bit different. Let's go down to number 5 here in your notes. What is the K value on number 5? 0 plus 0, so you could add that on. And again, now we have an A value. We have a number out in front. I'm going to go ahead and box everything up to the X there, and that's the core that I'm going to start with. And I want you to think about this as a -1 times the log base 2 of X. So, my little ordered pair here, what values am I going to, what's the first X value I'm going to use? 1, and then the B is 2, okay? Now, I'm going to plug in my 1. I'd have -1 times log base 2 of 1. What is the log of 1? 0 times -1? 0. All right. Now, if I plug in a 2 to my core, I'd have -1 times log base 2 of 2. What is log base 2 of 2? 1 times -1? -1. All right. What did the negative do to the graph? It flips it now, okay? So instead of starting low and ending over here, we're flip, okay? So we are at 1, 0, and 2, -1. So now my graph got flipped upside down. And now I can shift my graph. How does it get shifted? Right 2, up 0. So I'm just going to go right 2 and plot my point. Right 2 and plot my point. What happened to my vertical asymptote? It shifted right 2 as well. So my vertical asymptote is at X equals 2. And then I can graph my log ride. My falling down log ride. My asymptote is a vertical asymptote at X equals 2. What's my domain? 2 to infinity, beautiful. And the range? Yeah, -infinity to positive infinity. All real numbers. Yes, you could just do the boldface R. Same thing. All right, questions on that? No, it's pretty good, right? Pretty easy. All right, let's look here. Let's go ahead and put a 2 in front of number 6. So again, I have my core function here. I'm going to make my little XY chart, and what am I going to use for my X values? 1 and 4. 1 and the base, whatever the base happens to be. All right, so we have 2 times the log of 1. What is twice the log of 1? 0. Yeah, the log of 1 is 0. 2 times 0 is 0. And then I have twice log base 4 of 4. Log base 4 of 4 is 1. Times 2 is 2. So we have the ordered pair 1, 0, and then 1, 2, 3, 4, up 2. So here is my slightly taller log ride. Vertical stretch, and then how do we shift it? Left 5, down 2. Very good. So we're going to go left 1, 2, 3, 4, 5, down 2. Left 1, 2, 3, 4, 5, down 2. What happened to my vertical asymptote? It always shifts with the graph. So it moves left 5. 1, 2, 3, 4, 5. Yep. So that, because when we shift, our asymptote shifts as well. So if we shift left 5, that asymptote is going to move left as well. And then we can connect our nice little curve there. All right. So the asymptote is x equals -5. What's the domain? -5 to infinity. Beautiful. And then all real numbers for the range. Yep. Great.
No, I watched a video on one of the notes I missed.
I have to do one like this here as well. This came up in Delta Math as well. I thought that was pretty interesting. Here we have a -x. It's kind of interesting. But I have a core function here. And I don't think, maybe I want to change this to like, I don't know, a 3. Let's change the base to a 3 and so it's not a half. So there's my core function. And this is a little tricky because of that negative with the x, the negative in front. It's not a plus or minus, it's a times the x. So this is a little bit different. I can't do just a plain old 1, and I'll tell you why. If I try to do a plain old 1, then I'd have, log base 3. I'm going to pretend it's a base 10 for a moment. Log base 10 of, I'm plugging in a positive 1 for the x, so it becomes -1. And watch what happens. Oops, we can't do that. Yeah. So instead, I want to use the opposite value. I want my x to be -1. Watch what happens now. So I have log base 3 of the opposite of my x value, the opposite of -1, which gives you the positive 1. And now, what's the log of 1? 0. Okay, so you have to use an opposite x value. What am I going to use for my second value? -3. Very good. It's telling me to use the opposite x value. So this becomes log base 3 of the opposite of -3. And opposite of -3 is +3, which does give us our +1. What is happening when that x value is negative? It flips. Yes, it's flipping horizontally. So my curve, which started low and ended over here, is now, whoop, it got flipped over that way. All right, so we are at -1, 0 and -3, 1. So now my graph is going to the left instead of to the right. It still has that vertical asymptote at 0, but how does it get shift? Yeah, this one just goes up 3. Yeah. And that vertical asymptote didn't shift off of 0, it stayed. So here our vertical asymptote is still x equals 0, but what is our domain now? -infinity to 0, very good. And then the range is still all real numbers, yeah. All right, how do you feel about that? Do you feel pretty good? What about this kind? This is the last one we're going to do. It is a natural base, so instead of natural log, we could write log base e of x, log base e of x. And so we can graph in much the same way. I have my little xy chart. What am I going to use for x? 1 and yeah, not quite 3, or e, really, we're going to use e. So if I plug in my 1, I'd have 3 times the log base e of 1. Again, what is that going to give you? 0 every single time. And then 3 times log base e of e. What is log base e of e? 1 times 3? 3. And so we have the point 1, 0. And what is e? Not quite 3, so we're in between 2 and 3. And then up 1, 2, 3. So right about there. So again, this is a stretched logride. It's still a logride. It's just being stretched taller. And then how does it shift? Right 1 or down 1? Down 1, yes. This is down 1. There, which means that there's no h. There's nothing to put in parentheses, in other words, yeah. So we're going to go down 1, down 1. And there you go. Any questions? Okay. Delta Math has a really cool graphing tool. You do have to do it in the right order. So, at least I think it is. I'll maybe show you one. That's not too bad. It's 21 minutes.